So, to calculate the sine curvature kappa of this unit speed plane curve, we're first going to take gamma prime of s, and this is just going to be x prime of s, comma y prime of s. And I'm going to just start omitting the s dependence from now on. Notice that these primes are all derivatives with respect to s, which is the parameterization of the curve, and it's an arc length parameterization because this is a unit speed curve. Okay, so we know that since it's unit speed, then actually this is going to be x prime, and y prime is going to be plus or minus the square root of 1 minus x prime squared, just because this vector has to be of unit norm. Okay, and then we can now calculate gamma double prime, and gamma double prime is just going to be x double prime, and then over here we're going to be left with a minus plus x prime x double prime over the square root of 1 minus x prime squared. So that's just taking the derivative of this square root function here with respect to s. And now we look at the curvature kappa, which is going to be the magnitude of this second derivative, gamma prime, and we're taking the signed magnitude with respect to the direction, which is the 90-degree rotation of the tangent vector. So we rotate the tangent vector by pi halves counterclockwise. Okay, so what this is going to end up looking like is it's going to be the inner product of gamma double prime, and then, so I'll write it out. X double prime minus plus x prime x double prime. Okay, so there's gamma double prime. And then we're taking gamma prime, we're going to rotate it by pi halves. So this is going to give us negative y prime and then positive x prime. Now y prime, y prime we've expressed in this form, so it's minus plus square root of 1 minus x prime squared. Okay? I think that, yeah, that's correct. Okay, so now we're going to take this inner product. So we should be left with a, when you take this inner product, we have a 1 minus x prime squared times x double prime over square root of 1 minus x prime squared plus x prime squared x double prime over square root of 1 minus x prime squared. So the numerators, once you find the common denominator, the numerators will cancel, and we'll be left with a 1, just an x double prime, and then a minus plus, and then the common denominator, square root of 1 minus x prime squared. Okay, and then this is only well defined when y prime is non-zero. In the case that y prime is non-zero, we recognize that y prime is plus or minus this expression, so bringing the minus plus downstairs, we can just identify this as negative x double prime over y prime, okay? Assuming that y prime is non-zero. And then the identical calculation follows by symmetry, interchanging the roles of y and x for this expression. So in particular, we would just do the same thing that we did up here, but we'd write x prime as the square root of 1 minus y prime squared, rather than expressing y prime in terms of x prime. Part B, there are two things we need to show. First, the angle between the tangent vector and the horizontal axis is given by this expression, the arctangent of y prime over x prime, where by convention we're going to take that if x prime is 0, then we're taking the theta to be pi halves, okay? And in general, theta will be within 0 and pi, and so the piece of the arctangent function. Remember, if we look at the tangent, sine theta over cosine theta, this is going to go to 0 pi halves, and we have this expression here where negative pi halves here, so pi halves, yeah, we should have something like this, and then like this, here's pi, and then this is the branch of the arctangent function that we're taking here. Okay, so we're taking this branch of the arctangent, so what that means is we have 0 pi, and then right, so we have something that looks like this, I believe. Infinity coming up. Yeah. Yep. Okay, so this is the branch of the arctangent that we're taking in this definition, and then we're assuming that if x prime is 0, theta is pi halves. Okay, I should specify that this x-axis here is y prime over x prime, and the y-axis is theta, and this is just the graph of the arctangent function. The branch of the arctangent that we're considering. Okay, so remember we showed in the previous problem that we have such an equality here, where the curvature is just the derivative of this angle, the angle between the tangent vector, the curve, and the horizontal axis. Its derivative with respect to the arc length parameter. So, I'm going to take this derivative. The derivative of the arctangent, so recall that d over dx of arctangent of x is 1 over 1 plus x squared, I believe. Yeah, that looks about correct. So here we're going to have 1 over 1 plus y prime over x prime squared, and then taking the derivative of the inside, we'll express that on the numerator. The derivative of y prime over x prime is going to be y double prime x prime minus x double prime y prime, all divided by x prime squared. So bringing that x prime into the denominator, we're left with y double prime x prime minus x double prime y prime over x prime squared plus y prime squared. And we have a unit speed geodesic, so the denominator is 1. And that's the end of the problem.